Hello, we're going to go over AP Chemistry, Chapter 5, Section 6, Mixtures of Gases and Partial Pressures. Many gases are not pure, but are mixtures of gases. Partial pressure, capital P sub N, is the pressure due to any individual component in a gas mixture. And the way that we calculate that is by taking the number of moles of that gas and multiplying it by our ideal gas constant, the temperature, and dividing by the velocity. So in a mixture of gases, if you have gases A, B, and C in the mixture, the partial pressures are going to be, so the pressure of gas A is the moles of gas A times RT over V. The pressure of gas B is the moles of B times RT over V, and then you can see C right here is the same thing. So that was one way of calculating it. Also, though, the sum of the partial pressures add up to the total pressure. So if we know some of the pressures and the total, we can also find the partial pressure using subtraction. Here's an example for you to try. If a balloon is blown up to a pressure of 750 millimeters of mercury, and it contains the gases nitrogen, oxygen, carbon dioxide, and water, and their pressures are 580 for nitrogen, 142 for oxygen, and 20 for CO2, what is the pressure of H2O in the balloon? We're going to use subtraction to find the pressure. So since we know that P total is 750, and we have the pressure of N2, which is equal to the pressure of N2 plus the pressure of O2 plus the pressure of CO2, and lastly the pressure of H2O. We can plug in our knowns and solve for the water that we're missing. So we have 750 is 580 plus 142 plus 20 plus the pressure of water. And so to solve for this pressure of water, we're just going to subtract all of these. Pressure of H2O, I'm moving it to the left side of the equal sign, so I'm just flip-flopping the two around here. Okay, so if you add these together and subtract it, you are going to find that the pressure of water in this balloon is going to be 8 millimeters of mercury. All right. And yet another way to find partial pressures is using something we call the mole fraction. So it's just a ratio of how many moles of the individual gas you have over the total moles of gas. And to find the partial pressure, you take that mole fraction and multiply it by the total. So let's do the conceptual connection. 4.2, which is found on page 216. A gas mixture contains an equal number of moles of helium and neon. The total pressure is 3 atmospheres. What are the partial pressures of helium and neon? Okay, so the partial pressures, to find those values, we're going to have the pressure of helium is going to be equal to the moles of helium over the moles total times the total pressure. Okay, so, and then the pressure of neon is the moles of neon over the total moles times the total pressure. The total pressure here is going to be 3 atmospheres. And since it said these are present in equal amounts, that means that both of them are going to be half. So whatever the moles of helium is, that's equal to the moles of neon. And then when you add them up together, you're going to get, so it would be, let's say it's X, it would be over 2X. So the X's are going to cancel, and it's going to be 1/2. So both of them have a mole ratio of 1/2. A mole fraction of 1/2. So we can write 1/2 or 0.5, doesn't matter. Either way, our answer is going to be 1.5 ATM. Good job, those of you that got it. All right, let's try another example. So in this mixture, we have a 1 liter mixture of helium, neon, and argon. The total pressure is 662 millimeters of mercury at 298 Kelvin. The partial pressure of helium is 341, and neon's partial pressure is 112. What mass of argon is present? So we're going to have to go from the moles to the mass present in that sample. So how do we find the moles of argon that are in that sample? We are going to first find the pressure of our argon. Okay, so we know the total. Over here. So P total is all of the parts added together. So we have our helium, doesn't look like an H, plus neon, plus argon. Okay, capital P. And so the total pressure is 662 millimeters of mercury. And then it equals 341, that's the pressure of helium, millimeters of mercury, plus 112 for neon, plus argon's pressure, which we don't know. So moving that to the left side, I'm going to add these two together and subtract, and I'm going to get clear, or I can do 662 minus 341, 41 minus 112 is 209. So the pressure of argon is 209 millimeters of mercury. Okay, and so how is that going to help us? So to get to the moles of argon that we have present, since now we know the pressure and we know the temperature and we know the volume over there, we're actually going to use Pipnert. Okay, let's move this out of here. So we have PV equals nRT. To get to grams, which is what the question is asking for, we have to find these moles. So we can plug in the partial pressure and the partial, the moles, the temperature, and the ideal gas constant here. So we have 209 millimeters of mercury. We need to first convert that. So let's change that to atmospheres by multiplying by a ratio where I have 760 millimeters of mercury, 1 ATM. And if I divide those, I'm going to get 0.275 ATM. So this is my pressure of argon in atmospheres. Okay, and if we plug in the rest, we are going to get that 0.275 ATM times the volume, which is the total volume, because they're going to take that up, they're going to fill up whatever container you put them in. So it was 1 liter, 1.00 liters. That's our V. N is what we don't know. We don't know how many moles are in there. R is going to be our 0.08206. I'm going to leave the units off just to shorten a little bit. And then the temperature it gave us was 298 Kelvin. All right, so solve for N. If we multiply these two together and divide by these, we're going to get 1.125 times 10 to the negative second moles of argon, but it asked us for grams, so this is an easy moles to grams problem. So we need to go moles to grams. We're going to take our moles. There's the one in there. 1.125 times 10 to the negative 2 moles. Argon over 1. 1 mole of argon has a mass of, you look up the molar mass on the periodic table, 39.95 grams. of argon per mole, and we get 0.449 grams of argon in this sample. That is really messy. You guys get the idea. Okay. So that was a really challenging problem. That would be one of the more challenging ones I would have seen that are possible on the test. And for practice that goes with it, we have a sample of hydrogen gas mixed with water vapor. The mixture has a total pressure of 755, and the water vapor has a pressure of 24. What amount in moles of hydrogen gas is contained in 1.55 liters? So in this one, we're looking for the moles. Very similar setup. Go ahead and try the problem. Okay, so we have our pressure of hydrogen is going to be the total pressure minus the pressure of the water. Okay, we don't want that water vapor to be part of our pressure there since we're just focusing on the hydrogen. And we have 755 torr minus 24. Torr equals 24, 731. So that is my partial pressure of hydrogen, and we're going to use the same setup. So we have PV equals nRT. I'm going to go ahead and rearrange this for N. So N is going to be PV over RT. Okay, we just divide both sides by RT. Those would cancel and they move over here. And my pressure this time is 731 torr. Oops, let's change that to atmospheres. 731 torr over 1. 760 torr 1 atm. This torr is going to cancel. And the pressure of this is going to be divided by 760.9618 atm. Okay, so we're going to plug that in over here. We have 0.9618 atm times the volume. The volume over here is 1.55 liters in the problem. R is 0.08206 liters times atmospheres over moles times Kelvin. And then the temperature, 298. Okay, so let's go ahead and plug that into our calculator. I have that value times 1.55 divided by 0.08206. I'm going to hit equals. And then we still have to divide by 298. Equals. And so our number of moles is going to be 0.06097 moles. Okay, for significant figures, let's look over here. It looks like the 24 torr might limit us to 2 sig figs, so that would be 0.061 moles of hydrogen gas. Right? And we have a couple more problems to do. A diver breathes a heliox mixture, that's helium and oxygen. The mole fraction of oxygen is 0.050. What must the total pressure be for the partial pressure to be 0.21? This sounds a lot tougher than it is. So we're actually going to use the equation from back here. So we have the pressure of our gas, which is O2 that we care about. That's going to be the X is our mole fraction of O2 times the total. Okay, so we have this mole fraction here, the moles of O2. Let's write that out. The moles of O2 over the total moles, and that's not minus, that's equals. Okay, and they make it this weird X to not have it look like you're multiplying or like you're using X as the variable here. All right, so we're going to plug in our values. The pressure of O2 they give us is 0.21 atm, and the mole fraction is 0.050. We're going to multiply that by the total, and they want us to find the total pressure. So all we're going to do is divide by this 0.050 on both sides. Okay, those will cancel out, and the total pressure has to be 0.21 divided by 0.05 equals 4.2 atmospheres. Okay, which is reasonable for a diver. All right, so lastly, collecting gas over water. We have zinc metal reacting with hydrochloric acid, and when zinc is attacked by HCl, hydrogen bubbles off. So the hydrogens will come together and make hydrogen gas, and you can see the little H2s going through the tube, and they're going to collect it over here in this beaker over water to keep the gas from escaping. So what we have is we have some little water molecules that are going to end up above the water line with the hydrogen mixed together. So we have a mixture of gases up here. And so what we're going to see is if we want the pressure of just H2, we have to subtract the water pressure from that. Okay, and the vapor pressure is the partial pressure of water in that mixture. The vapor pressure depends on temperature because the warmer the water, the more molecules will be able to escape the surface and go into the vapor phase. Okay, so we're going to use this chart, which is in your book on page 219, to look up the partial pressure or the vapor pressure of water at various temperatures. Okay, so in order to determine the rate of photosynthesis, the oxygen gas emitted by an aquatic plant is collected over water. So we have a little plant giving off oxygen, and we're going to collect the oxygen above the water at a temperature of 293 Kelvin. So that's going to be significant because we have to look up the vapor pressure at 293 and a total pressure of 755.2 millimeters of mercury. Over a specific period of time, a total of 1.02 liters is collected. What mass of oxygen forms? This is similar to the ones that we were doing earlier. Okay, so we need to find the pressure of the oxygen, and that's going to be the total pressure minus the pressure due to H2O. Okay, so the total pressure is at 755.2 millimeters of mercury, and we're going to subtract 293, that would be 20 degrees. 20 degrees, the pressure is going to be 17.55 millimeters of mercury, which means the pressure of O2 is going to be 755.2 minus 17.55. $737.65 millimeters of mercury, and let's go ahead and change that right to atmospheres. Divide by 760, and we get 0.97059 ATM. as the pressure of our oxygen. Okay, so we had to subtract that water vapor, and that's why this was significant to this one. Whoops. Okay, so the temperature, so that's our pressure. The temperature is 293, and we have a volume of 1.02 liters. So we have P, we have V, we have T. Whoopsies. Hopefully we can finish this one because it's the last one. So we're going to find our PV over RT. That was our equation for N, which we used up here. PV over RT. Okay, and the pressure is going to be 0.97059. The volume is 1.02 liters. And R 0.08206. And then lastly, temperature is 293. I'm going to plug in so that we can finish this up without it shutting off. Sorry guys, bear with me for 1 second. One more second. So we can calculate the number of moles that way. So we have this value times our 1.02 equals, we're going to divide that by 0.08206 equals, and divide by 293 equals, so the number of moles of O2, 0.41175 moles, but it asked us for grams, so we're going to go from moles to grams. 1 mole of O2 is 32 grams. So over here, times 32 equals, and our grams, the mass of O2 is 1.3. How many sig figs do we have over here? Looks like we have 3 sig figs. So it's going to be 1.32 grams of O2 from photosynthesis. All right, and we are done. Thank you guys, and I hope you have a wonderful day.